everybody. I am Kyle Bader, Principal Portfolio Architect for Ceph offerings at IBM. Joined with me is my esteemed colleague here, Uri Wasserman, Distinguished Engineer. And today we'll be talking about the new NVMe-over-Fabric target that we have for Ceph. So what is Ceph? Well, there's a lot of kind of buzzy type ways to say it, but essentially it's storage software that's open source and distributed storage system. One of the key things about Ceph is it's really designed to run on commodity hardware, right? So it's IP networks, conventional disks, generally not like special purpose hardware. It's open source, it's free in that respect, and it has a wide and thriving community. You know, we have contributors from all over the world, from a number of different companies, both kind of people that build components, software companies, and then of course practitioners as well. And the whole premise of it is to be able to build something more than the constituent parts. So you don't need to have kind of like mainframe-esque hardware or really high availability hardware. You can kind of take general purpose hardware and create something that's more reliable by using replication and erasure coding. And Ceph, over most everything, values consistency and correctness over just trying to be the fastest. So if there's ever comes to a point where we're trying to make a decision around whether we should we relax consistency, or could we get away with this most of the time and it would be faster? We usually don't take that approach. We usually favor the consistency and the correctness. Part of the core of Ceph's DNA is making it scalable. It's kind of the object approach, using algorithmic placement, and this idea that you can scale up with faster hardware, you can scale out a cluster by adding more, and we have some federation capabilities for when you have multiple clusters, so you can do kind of a cellular design or multi-site design. And Ceph does, it's not just block, it's not just file, and it's not just object. It kind of has its own native API, and then on top of it, there's a number of different abstractions. So you can consume it through S3 APIs, you can consume it as a virtual block device, or as a distributed file system. Drivers for block and file, and the Linux kernel for 2.6, 2.7 or something. So down at the lowest level is Rados. So Rados is object storage API of itself, but it also designs a scheme that's a little bit more than that. It's a little bit different than most object stores. It has strong consistency. It manages the actual erasure coding, data placement, rebalancing, and it has some additional things, like when people think about object storage, they also often think about something that's like CRUD, where you can do creates, updates, deletes, etc. But you can actually do kind of write to arbitrary offsets in the object store. There's this whole like class operations where you can write classes so that you can kind of do computational storage type things. And then oftentimes these are used to build kind of higher level abstractions like the S3 object storage. And then there's also notifications on that. So this is kind of just a brief overview of Ceph before we jump in. In every Ceph cluster, there's always 3 components. Those components are OSDs. OSDs are usually a one-to-one association with the actual physical media. And then it's a software process that runs in Linux. And then the OSDs basically work with their peers to distribute the data, and then the clients interact with them directly. And then kind of the monitor is Quorum, uses Paxos, and you can think of it as coordinating the cluster and deciding groups of OSDs and which ones should communicate with each other for the different placement groups. And then there's the manager, which we've kind of, originally that functionality was in the monitor and we peeled it off into its own process. It does some things like perf counters and some of our, there's like a pluggable management framework so that you can, write different plugins to do different sorts of management things. Kind of a departure from a lot of different storage technologies is actually client to cluster. So the actual native Ceph client is you have direct access to the storage. So kind of think of it almost like a PNFS type thing, but it's a kind of a sophisticated object protocol as opposed to a file protocol. And yeah, so you can either code directly to Liberatos, which is an object storage API, or you can consume one of the block file or object interfaces that's built on top of Liberatos. On the block side, so if we're peeling back how our virtual block devices work inside of Ceph, inside of Rados, we basically take the range of the block device, and then we stripe it across a bunch of 4 megabyte by default Rados objects. And so these get distributed across the cluster. Tends to be kind of a normal distribution, and then we have some weights that we can do to tweak it to move it towards a more uniform distribution. That way you get balanced usage out of the hardware and then tend to get balanced performance as well. A lot of people will have a dedicated storage cluster, or even if they're running it converged with their hypervisors, then they don't have to worry about moving data around if there's loss of a hypervisor, because it's kind of this shared, decoupled thing. Implemented, like I said, in the Linux kernel. It's been there since 2.6, 2.7, maybe earlier, for block and file. There's also native integration in, for example, KVM QEMU, and that's done through virt.io. In terms of kind of higher level, OpenStack, Kubernetes, OpenShift, really popular to consume the block device. We wanted to take and bring our virtual block devices to people that weren't necessarily going to be consuming them from Linux systems. And so one of the things we initially looked at was doing this via iSCSI. And so we do have an LIO stack that works with our librd block, and in conjunction with user space tools to kind of set up iSCSI gateways. And we had some people that were starting to use this, but new protocols and we're kind of late to the iSCSI game, and we saw a lot of interest around being able to consume RBD from NVMe-over-Fabric. And so that's what Orit is going to talk with us about, is the development of our new SPDK-based NVMe-over-TCP target.
Hello, I'm Orit Wasserman. I'm a distinguished engineer in IBM, and I'm the lead architect for NVMe TCP for Ceph. So I'll go really briefly over what is NVMe-over-Fabric. So we have NVMe, it's PCIe attached, and as it's really, when you look at it, it looks like a network protocol. So it makes sense. We want to do it over Fabric and have disaggregated storage that you can access over different fabrics. The first fabric was introduced was actually RDMA, and then Fiber Channel, and then TCP. Maybe in the future, others as well. And then NVMe over TCP was ratified in 2018, and since then we have lots of advanced adoption, and it's become very popular. So the base is very similar. We have controllers with the queues for NVMe, and it's shared across the NVMe's and the connection binding is part of the NVMe-over-Fabric. So as Carl mentioned, we already have iSCSI. Why did we stay with just like iSCSI and are working on doing an NVMe-over-Fabric gateway? So while iSCSI is a mature, I didn't want to say old protocol, so it's a bit a legacy, and new applications prefer NVMe-over-Fabric. And if we compare performance, NVMe-over-Fabric is better. It has higher throughput in IOPS, lower latency. It also uses less CPU, and it's also much more scalable. So we want NVMe-over-Fabric. But why Ceph needs a protocol like NVMe-over-Fabric? We have our own block protocol, RBD. And the reason is that to use RBD, you need a client. And it's not always available, or sometimes the user doesn't want to use a Ceph client in spite of the fact that, or maybe the operating system doesn't have the Ceph clients because it's proprietary, like Windows. In that case, we need the standard industry protocol, and NVMe-over-Fabric, that's one. It also, there are many use cases that NVMe-over-Fabric is using in the ecosystem, so it's much easier to adapt it, and it can use offloading that we have in the DPUs. So I think I convinced you why we want NVMe-over-Fabric. Let's talk about how we implemented it in Ceph. So basically, the architecture is architecture of a gateway. We have the initiator, standard industry initiator, can be operating system initiator or maybe hypervisor initiators. They all connect to the gateway, and that gateway talks to Ceph with the Ceph protocol. As you probably noticed, if before all the data path went directly to the Ceph cluster, here we had adding a hop on the wire. We're going to support many types of fabrics, but we, as Ceph is mostly commonly deployed with TCP, care mostly about TCP. But because we use SPDK, we'll have the built-in also support for the other fabrics. So how we'll map the NVMe component and Ceph. An NVMe namespace easily mapped one-to-one with an RBD image, a block image. Then when initial connects to a target, it connects to a specific subsystem. That system is a logical grouping of namespaces and is used to do basically access control. So we can make sure that initiator can connect only to subsystems that have the namespaces they can see. And each initiator can get one or more controller. Usually more means when we need higher scalability. First of all, we need actually to configure the gateway. So we need a control plane. We wrote it separately from the data path. It's written in Python as there's no performance requirement, and Python is much more easy to program control planes. All the gateway command and API are using gRPC. Who here knows what gRPC is? One. I love gRPC. So gRPC is general RPC, remote procedure call. I sometimes laugh that it's Google RPC because Google started it. And the idea is that instead of RPC that is in the same computer, it actually allows you to do really remote calls using REST API that are based on HTTP and HTTPS if you want encryption. And they use also protobuf. Protobuf are a programming language to define your protocols and API. And then you can either compile, depending on language, or generate the API in your favorite programming language, C, C++, Java, in our case, Python. And then during build time, you can actually test the protocol and API. It also provides backward compatibility and versioning, and all the response and requests are binary, so they are compressed, so it's very efficient. So I really like gRPC, and in Kubernetes world, this is the default way to create APIs. I really recommend. We also provide CLI, and the CLI will basically be implemented on top of the gRPC and connects with MTLS to the gateway. We want the configuration to be persistent. Configuration, for example, can contain the IP addresses of the target, the subsystems, also the mapping between the NVMe namespaces and the RBD images. It doesn't make sense that if the gateway restarts, we lose all that configuration. Luckily for us, we have a persistent, highly available storage that we can store the configuration in. So all the configuration is stored in Ceph, in a special object that we call OMAP, object map, and it's a special Redis object that allows you to have access of a key value store. So it's very easy for configuration, and also you can do watch notify on it, so get an event when something changed. This way we can even use it later to communicate between the gateways. So as Carl mentioned, we chose SPDK for the NVMe-over-Fabric target. So first step, we knew we need to implement NVMe-over-Fabric semantics and implement and map NVMe commands to Ceph RBD. That's a lot of development. I did it in the past. Quite complex to write an NVMe-over-Fabric target. And we are open source, so of course we looked around to see what open source options we have. There's a target in the kernel, but we wanted something user space because from our experience, developing a kernel can take a long time. If we need some changes, the cycle is longer. User space is much easier for us. And we found one. We have SPDK. It's actually much more than NVMe-over-Fabric target. It's a storage performance developer kit. It creates a framework basically to do very efficient user space I/O. But it also has an NVMe-over-Fabric target that supports TCP, RDMA, and fiber channel. And someone already added the support for Ceph RBD. In SPDK, we have BDEV RBD. BDEV is the SPDK abstraction of block device. And it's open source and compatible to Ceph. This is a win. So it shows SPDK. So how did the data path look? So we have a container that contains the control daemon in Python, and it basically connects and configures the SPDK running. Could be in a different container in the same node or in the same container, and configure it and use the RPC that the SPDK has to configure SPDK. All the data path goes directly to SPDK. The control daemon is not involved in the data path at all. So how does the mapping look from NVMe to RBD? So some of the commands were easy. We have them in RBD. Others we didn't have, and we need to emulate them in SPDK. So we have read and write natively in RBD. Unmap maps to discard in RBD. Flash we have in RBD. Write 0 we have in RBD. Compare write we had in RBD. It was actually emulated in SPDK. And the reason it was emulated is because it was limited. It was designed for a very small block size, not enough. And we had to extend it and change it that it can accept bigger 4K commands, and also change SPDK to call the RBD command and not the emulated one. This is all merged upstream and ready. And emulated, we use the code in SPDK for compare and copy. A board is more complex. SPDK has support NVMe abort, but in case with Ceph RBD, we don't have abort. So SPDK cannot return the command immediately. You need to make sure that all the pending IOs that were already sent to RBD completed successfully or not. And this makes the abort command can be quite a long command, which is not what was planned in the spec. When there will be NVMe cancel, we will look in the implementation to see if we can improve it. So we have a gateway, it's running, everything is fine. So the Ceph, as Carl mentioned, is all about reliability. Everything is reliable. We do wider replication or erasure coding of the data, and it has self-healing. But our gateway becomes the single point of failure, because every I/O and everything goes through the gateway. So we need highly available gateways. Our solution is to use a gateway group. So a group of gateways basically will allow the initiator to access the same namespace, the same RBD image, and we'll use NVMe-over-Fabrics ANA, asynchronous namespace access, to define an optimized path, a single one, and non-optimized. So in case the optimized path is not available, the initiator can automatically switch and use the non-optimized. You can also use the gateway groups for scaling or load balancer. In some cases, a single gateway cannot give enough IOPS for several initiators using the same namespace. In that case, we can use more gateways that allow access to the same namespace without high availability. Basically, all will be optimized. So those are all the things we have. Now I'm going to talk about what we are still working on. So first of all, you noticed I didn't mention discovery. Discovery is very important in NVMe-over-Fabrics. It's really simplified the uses. You don't need to know the IP addresses of the target. So we're working upstream on adding a discovery service. We could not use the SPDK one because it only knows the subsystems that gateway is handling. But we want in a discovery to return all the target and subsystems that are in the Ceph cluster. This is work been going on upstream by Intel. And we have a new discovery in Python. And in the beginning, the thought of reusing SPDK, doing like a thinner SPDK just for discovery, but it didn't work, and we decided to go with the new gateway in Python that just implement the discovery NVMe commands, the get log page. It's stateless. Basically, every time you ask for a get log page, he reads the configuration of the different gateways from the Ceph cluster and returns all the information. Next is authentication and encryption. So Ceph has built-in a feature that all the traffic between the Ceph components and RBD are encrypted. But we need to handle the encryption also between the initiator and the gateway. We decided to go with IPsec or VPN. This actually gives the responsibility to the user and not on us to do the encryption. The user will need to set up the IPsec tunnel and make sure all the credentials are passed. And also, if you notice, this doesn't handle any authentication because IPsec doesn't pass identity information. We are planning to support the NVMe inbound authentication in the future. We just felt that it's a bit premature now, not really supported in different initiators. So we're still waiting on that, but that's the plan in the future to allow much better granular authentication. Currently, our authentication is basically by using the subsystems to do access control and the fact that the initiator will need to know the IP addresses of the target. We want to add quality of service. SPDK has built-in quality of service. You can define the limits for IOPS per second, for namespace, bandwidth, read bandwidth, and write bandwidth. You probably noticed that it will be a problem if we do a gateway group that allow access for the same namespace for different gateways. We don't plan to, at least there's no future plans to handle that for gateway groups. If any one of you want to volunteer to do it, we'll be happy to get your help. But it's quite complex if you think about it. It means that they need to somehow synchronize the IOPS and everything. VMware support. So one of the main reasons Ceph has high SCSI support was to support VMware. VMware doesn't support Ceph clients and only use the industry standard protocol. And they have VAA. VAA is vSphere API array integration. Those are basically 4 commands that the storage have to provide so vSphere can run using that storage. The first command is atomic test and set. This is supported in NVMe-over-Fabrics by the compare and write command fuse. That means it happens in the same command. This is currently already supported. We had, as I said, issue with the size. Xcopy is external copy. This is basically implemented by SPDK copy command. Write 0 goes to RBD, and unmap is RBD discard. We have already running, and we tried, and everything looks well with vSphere. Oops. Okay. Another work going on quite a while is adaptive distributed NVMe-over-Fabrics namespaces, or in short, ADNN. As I talked, the gateway model.
Could you explain a little bit more why the copy NVMe command is supported by SPDK? What do you mean by that?
Sure. So SPDK doesn't call RBD copy command because it does it on its own. He emulates it. Yes. So ADN, so the gateway adds additional op on the wire to access, and basically we lose all the distributions of Ceph that allows large high throughput by the fact that the single client can access multiple OSD nodes at the same time. So the idea is to collocate the gateway with the OSD. In the current distribution, that Ceph really likes to do uniform pseudo-random distribution, the chances that the IO you're doing actually will be for the same node is quite small. We have lots of OSD in the cluster, and most likely you need to read the data from another OSD. So one thing we'll need to do is to limit the distribution of the data to less OSDs. Not all the OSDs on a cluster, but only for the OSDs who have a gateway on. And the other part is actually for the initiator to know to which OSD to go to. Of course, the initiator cannot run the Ceph quite complex placement algorithm called crush. It's quite heavy, and it's not needed. So the idea is not to do that, but have a very small, much simpler routing table and providing hints to the initiator to where the data placement is. And of course, if there's a mistake and the data goes to the wrong node, he can forward it to the right node and tell the initiator you need to update its routing table. This is being talked in the NVMe Express for a while. I don't know what the status is, if it's going to be ratified soon or not, but it's been, so someone here is saying no. I don't know. Scott Peterson from Intel is really pushing it. He actually did a presentation in SDC here a few years back. I really like the idea, but as standards go, it's probably complex. You need to fit it probably to many storage systems and so on. So let's talk about performance. So this performance setup is not to showing how good Ceph is or the NVMe-over-Fabrics gateway. We just wanted to see that the fact we added this new gateway won't hurt our performance more than it was before. Our setup was quite limited. It's only 3 node clusters and not much CPUs. 3 nodes is also the minimal Ceph cluster. We actually don't support it for production. We recommend at least 4. So ignore the max numbers. It's more about to seeing the cost of our NVMe-over-Fabrics gateway. So on the left, we see it what we started, and on the right, it's what we ended, which is much better. The beginning, we were probably less than half, not very good. And we improved our setup and changed. Few things we had to do. First of all, is CPU pinning. So at first, we ran SPDK and BDEV RBD on the same core. We noticed it's not working good, so we actually split and give a different CPU set for SPDK and leave RBD so that they won't compete with each other. Another thing we did is actually change the Ceph number of Ceph clients. So we looked at we started with a single Ceph client for an SPDK target. That what became a bottleneck. So we looked at what if we increase the number of Ceph clients, how can the performance is improved? And as you can see, with 16 Ceph clients, we can almost get to the line rate. Small comment, this is with OSB-backed param disk, so this is just to test the SPDK performance and our setup, not to test Ceph. There is a cost for Ceph clients. Ceph clients, each Ceph clients have 5 threads and opens connection to all the OSDs in the cluster. If you have too many Ceph clients in the same target, you'll have lots of threads and lots of connection. At some point, if you have a fixed number of cores, that will be too much. And here we can see that the right number is around 8 Ceph clients, but no more. 16, you can see sometimes the more cores you have, you can actually have drop in the performance. And I have to say thank you because the NVMe-over-Fabrics for Ceph is a community effort. We had contributed from many companies, and the biggest ones is Calixto, IBM, Intel, and Red Hat. I want to say a special thanks to Jonas from IBM Research, who led the prototype for the NVMe-over-TCP fabric and helps a lot with the architecture. Ilya, the RBD maintainer, will give lots of input and make sure everything works correctly. All the team in IBM and the team in Intel that works on discovery, and Scott that provide lots of input. And if you want to join, which is one of the effort, you can join by just helping us, or maybe take features we didn't look at, or maybe use the gateway and tell us our feedback. All the code is up in GitHub. We have our target here. And we have a weekly meeting every Tuesday at 7 a.m. So you can still make the team meeting just before the conference this week. And so come and join us. And I'm around in the conference all week. So if you want to chat, I'm here. Kali is here today. So thank you.